Good morning, everybody. I'm Marco Savi. I'm a researcher at Fondazione Bruno Kessler, which is a research institution in Italy. I specifically work within the CreateNet Research Center. We mainly work on the network, cloud, and IoT technology. What I want to show you today is the concept of programmable data planes and how they can be exploited to empower network monitoring functionalities. So, why is network monitoring important? I'm sure most of you know this. Network monitoring is a task that provides a view on the network stature and its actual behavior. So, with network monitoring, network managers can assure that the network operates according to the intended behavior, and so if there is a divergence with respect to the from the actual behavior with respect to the intended behavior, this can be solved. So network monitoring supports network management operations such as traffic engineering, quality of service enforcement, or anomaly detection. In general, we have two different kinds of network monitoring techniques, passive and active. With passive network monitoring, we check the traffic that is flowing into the network, and we try to collect information from this. While with active network monitoring, we inject probes in the network and collect information from these probes to see if something is going wrong or strange. In this talk, we specifically focus on network flow monitoring, which is a passive technique and which consists in looking into the network flows in the network to understand whether something is going wrong. So, what is the current approach to network flow monitoring? There are different kinds of protocols and techniques like NetFlow, IceFlow, and so on. NetFlow is the most well-known network flow monitoring protocol, but all these kind of techniques has the similar drawbacks, as I will show later on. How does NetFlow works? So NetFlow requires to have a NetFlow-enabled device, a router, okay, which every time a packet comes into my router, what I do is I inspect the packet, I take the information I need from the packet header, and I update statistics in the NetFlow cache. So for example, if I have a flow and a new packet is coming for an already existing flow, I update the counters. Otherwise, I add a new entry. So what we have here is a huge number of counters for each flow in the network. And periodically, this information is sent to a NetFlow collector, which then computes statistics and check if things are working. So which are the well-known drawbacks of this approach? First of all, this has high load on hardware, leads to high load on hardware equipment. This mainly because it requires a lot of computational power to do this kind of operation for each one of the packet, and then it has a very low time granularity, since usually this information is sent typically every 5 minutes to the NetFlow collector. Why? Because otherwise they flood the network with information, monitoring information, and this is something that I don't want to do. So to overcome these issues, sampling is used. What is sampling? Just taking 1 over 10, 1 over 100, and so on packets and do this kind of operation only for those packets. Of course, this reduces accuracy, which is a problem. So here, programmable data planes come, since they can help improving network flow monitoring performance. So what are programmable data planes? Probably you have heard about it. It's new technologies that bring advancement to the SDN paradigm. With programmable data planes, what we need is a device data plane which is programmable, and I can configure this device data plane by means of a configuration program which is compiled and injected in my device data plane. So in this case, I can let's say, specify the behavior of my data plane in terms of filtering, monitoring, and processing capabilities. So why is this relevant? This is relevant because it increases the flexibility in the, let's say, support of new protocols, since if I want to support a new protocol or a new functionality, I just write a new program, and I compile it, and I, let's say, inject the code, let's say, in the device data plane. So it leads also to a more efficient usage of resources in terms of memory and CPU, because I make the device data plane do what I want it to do. And of course, it follows the software-like design and development cycle. If I want to add a support to a new and innovative protocol, I just have to write a new piece of code. So there are many solutions have been explored on this. We focus on two in this talk, which are P4 architecture and extended Berkeley packet filtering, eBPF. P4 is an architecture, P4 architecture is for switches, so it's best suitable for in-network packet processing, while extended Berkeley packet filtering is most suitable for Linux-based end-host devices. So, you know, the domain it's most suitable is the one of the edge of the edge of the network. So, in few words, how P4 switches work? Okay, P4 switches rely on the so-called PISA architecture, protocol-independent switch architecture. Here, the two main components of a P4 switch, which are the parser and the P4 pipeline. The parser tells you how the packet should be parsed when they go inside our switch, which are the protocol I expect to find, and how the packet header, the fields of the packet headers should be extracted. While the pipeline is a concatenation of match and action tables, which can be configured and which can give my behavior, intended behavior for the switch in terms of packet processing, and also if we want of monitoring. So what you have to specify in the P4 program is a parser graph to tell the switch how to parse the packets, and the table configuration, so how to configure the pipeline. So in the pipeline, we can use header, intermediate results, and metadata to do matching and following actions, and the headers can be modified, added, or removed. This specific architecture is very suitable for network flow monitoring. At least there are two different techniques that can be implemented using this kind of architecture. One is in-band network telemetry that consists in adding an INT header to the packets and to add metadata in these packets, for example, in terms of hop latency, and then this information can be collected and monitoring can be performed. The second one, a bit probably less known, are sketching algorithms in data plane. Sketches are probabilistic data structures that can store a huge number of flow counters in a compact form and in an estimated way. But I have theoretical bounds on the estimation on the error that I can have. And we will go back to this later. So what is instead eBPF? eBPF is a Linux kernel technology. Specifically, it's a virtual machine that resides in the Linux kernel. An eBPF program is written in C code. Usually, it is compiled. The eBPF bytecode is inserted in this virtual machine. And here in the device kernel space, which is actually the data plane of my Linux device, we have the eBPF program, which is an event-driven program that is triggered every time a packet comes into my interface. So in this case, what I can do is different operations on the packet, like accessing them and collecting information, modifying them, or filtering them. So this is a very good approach, because this eBPF program is called before the packet reaches the TCP/IP stack, so I can do operations on the packet at a very early stage of this packet processing. An important concept here are the maps. Maps are these data structures that are used to store information for the eBPF programs, and they can also be accessed by the device user space. So also this kind of technology is very suitable for network flow monitoring, especially with respect to anomaly detection, as we will see later. So I've then prepared this table. I'm open to any argument against anything is written here, of course. But this is like a comparison between these two technologies in terms of program functionalities and features and so on. In terms of program functionalities, let's say P4 requires a domain-specific language. It is a C-like language, but it is a domain-specific language, while eBPF uses the C language. Memory allocation is static in both cases, while we have some limitations in the stack space and in the number of instructions per program with the eBPF, because we are constrained by the environment, which is the kernel space, while we do not have any limit for P4. Okay, we are limited by the underlying hardware, of course. Then loops and recursive functions are not possible in any of the two cases. Pointers are possible in eBPF, not in P4. Global variables and wildcarding are possible in P4 and eBPF, for example. So looking at the additional network functionalities, the deep packet inspection is not possible with P4, while it's possible with eBPF. Other functionalities like fragmentation of packet generation, important functionalities, in my opinion, are not possible in any of the two cases, while processing of packet trailers, if needed, it's not possible with P4, but it's possible with eBPF. Then there is another important aspect that is related to hardware. While eBPF runs on generic purpose hardware, it must be equipped with a recent version of the Linux operating system. Hardware, of course, for P4 must support the PIS architecture that I showed before. So now what I want to show you is a use case for the DOS detection and mitigation that can be done by using functionalities offered by these two different techniques, P4 and eBPF. So here we have two different scenarios. We want to filter packets that are coming from an attacker, from malicious sources, before they reach a victim. And with the DDoS attack, we have an attacker that compromises multiple slaves creating a botnet that all try to contact the victim, for example, a DNS server, and flooding it with a lot of traffic. So let's say, in this case, we have one specific destination IP address that is contacted by a huge number of source IP addresses. So to implement our DDoS detection and mitigation logic, I don't want to go too much into the technical details. By the way, we consider as a scenario a P4-enabled SDN network, so a network which is equipped with all P4 switches. What happens here, this is how we have configured the pipeline to do filtering of packets coming from malicious sources. So when a packet comes in, we take the IP header, we consider the source IP, and here we have implemented a sketch that is, let's say, this kind of data structures that I told you before to implement a source IP blacklist. So taking the source IP, I can tell whether this packet belongs to the blacklist or not. If it belongs to the blacklist, we drop it. Otherwise, we pass to the other stage, to the next stage. Here we check the destination IP address. In this case, we have another data structures, another sketch that is called the count min sketch that helps counting the number of packets that are going to any specific destination. We take this sketch, we compare it periodically, like every 30 seconds, with the previous sketches, and we see if there is some abnormal behavior, and we store the information related to this abnormal behavior. So every time a packet with a specific destination IP comes, we compare, let's say, the information related to this destination IP address to the information related to the malicious traffic. And if the destination is the one that we believe is under attack, we add to the source IP addresses this specific source IP to the blacklist, and we drop the packet. Otherwise, we pass it to the transmission. So this is a simple implementation, quite simple implementation in our in the pipeline for DDoS detection and mitigation logic. So, second scenario, we are let's say implementing our DDoS detection and mitigation is a scenario in which you have an edge node that hosts virtualized network functions, and that is connected to a DMZ where there is a DNS server. And we want to filter the traffic that we find it's malicious directed to this specific DNS server. So this is another algorithm, okay? And what we do here is injecting an eBPF program that does this kind of operation. When a packet comes in, we first filter it according to a specific source IP blacklist, which is implemented in a map. So if the packet belongs to the source IP, if the source IP belongs to the blacklist, we filter it and drop it. Otherwise, we pass to the next stage for feature extraction. Here, we extrapolate the source IP address and destination IP address for this packet, and we update statistics in two maps with respect to the destination IP addresses and source IP addresses. So we have a counter for source IP addresses and destination IP addresses here and here, one counter for each one of the source IP and destination IP that I can have. So periodically, what happens is that we do an entropy estimation. So if we are under attack, usually my destination IP address's entropy decreases while my source IP address entropy increases. We do this kind of evaluation, comparing also with the entropies for previous times. Also in this case, we usually set 30 seconds as time to do this kind of operation, which is done in the user space, by the way. If we detect that we are under attack, we add to the source IP blacklist all those source IP that contacts the destination IP with the highest number of packets. So, of course, then, okay, the packet is sent to the TCP IP stack for the capsulation and then delivered to the right user space application virtual network function. So this is another implementation that is suitable in an edge scenario. So, I want to conclude my presentation to just recap a bit the things. So we have shown that existing network flow monitoring techniques suffer from complexity or accuracy issues. So with programmable data planes, we can help reduce the complexity with limited impact on accuracy, while ensuring high performance. This is important because everything is done at line rate in the device data plane. So we have presented two different technologies that can be exploited for network flow monitoring: P4 and extended Berkeley packet filtering. Probably P4 is more known than eBPF at the moment, and while P4 is very suitable for in-network packet processing, eBPF is very suitable for edge packet processing. So we have presented a use case for DDoS detection and mitigation, and we have shown how we can exploit these functionalities for network monitoring purposes. To conclude it, okay, if you ask me which is better between P4 or eBPF, I cannot give you a clear answer, of course. In the future, if there will exist networks that are P4 enabled, so fully P4 networks, what network operators can do is like offering as a service this DDoS detection and mitigation or other functionalities to the service providers or whatever, and also to filter traffic that is malicious on their network for these two different cases. Of course, if a service provider, an edge provider or whatever, cannot rely on this kind of service, it has to implement this logic, this DDoS detection and mitigation logic at the edge, and in this case, eBPF is the most suitable solution. So this concludes my presentation. Thank you.